My name is Michael Ron Robinson, so I'm chairing this lecture this evening. It's a great pleasure for me to do that. The Institute of Physics Isaac Newton Medal was established last year to recognize international physicists. It's already one of our most prestigious awards. The terms of the award are that the award shall be made to any physicist, regardless of subject area, background, or nationality, for outstanding contributions to physics. And the 2009 award winner is Alan Guth for his invention of the inflationary universe model. And it's a very great pleasure to welcome him here this evening. Alan Guth was born in 1947 and did his PhD at MIT. After postdoc positions at Princeton, Columbia, Cornell, and the Stanford Linear Accelerator, he returned to MIT as associate professor in 1980. He's now Victor F. Weisskopf Professor of Physics there. In 2004, he won the Peter Gruber Cosmology Prize. He's the author of several books, including The Inflationary Universe, The Quest for a New Theory of Cosmic Origins. In 1980, working with Henry Tye, he realized that the standard cosmological model would produce catastrophic numbers of magnetic monopoles, and that supercooling at the ground unified phase transition could suppress these monopoles. He went on to devise a detailed scenario for this, the inflationary universe. And in his famous 1981 paper, which has over 3,400 citations, he pointed out that this would solve two of the outstanding metaphysical problems of cosmology, the horizon problem and the flatness problem. And I'm going to leave it to Alan to explain what those are. In the abstract of this paper, he modestly wrote, "Unfortunately, this scenario seems to lead to some unacceptable consequences, so modifications must be sought." Well, within a year, Lindy and Albrecht and Steinhardt had come up with new inflation, which solved these problems. Alan Guth's inflationary universe received a tremendous boost from the detection of the theory of fluctuations by Jacobi and WMAP, which conform to the predictions of the inflationary paradigm. One thing to say about Alan is he didn't just write the paper and stick it in, submit it to the journal and leave it there. He spent 2 or 3 years trekking around to giving seminars, speaking at conferences, trying to persuade people that this was a really important idea. And I remember hearing him lecture at that time. And I think it's a great lesson for young physicists that you don't just write the paper, you actually have to persuade people that this is important. Tonight, he's tackling 4 of the great imponderables: inflation, the multiverse, string theory, and the cosmological constant. So it's with great pleasure that I invite Alan Guth to give his lecture, his Newton lecture on inflationary cosmology. Is our universe part of the multiverse? Alan.
Thank you so much, Michael, for that warm introduction. I'm very pleased to be here tonight. I always enjoyed visiting England. I spent a wonderful day yesterday at Cambridge, and tomorrow I'll be visiting Oxford. And it's really wonderful to have a chance to see so many of my old friends here in this country. The work that I'll be talking about is work that really goes back to 1979. When I got into it, I was really purely a particle theorist. I had never worked in cosmology previously. At the time, myself and a number of other people got sucked into cosmology really through particle physics itself. This was the time when grand unified theories were first becoming an object of widespread interest. And what characterizes these grand unified theories, as you probably know, is the natural energy scale of about 10 to the 16 GeV. Now, by the standards of our local power company, that's not much energy at all. It's what it takes to light a 100-watt bulb for a period of about 4.5 hours. But if you try to imagine putting that much energy on a single elementary particle, which is what grand unified theories are all about, it really is an extraordinary amount of energy. One way of seeing how much is to imagine trying to build a particle accelerator that might reach those energies. We can do it with present technology in principle, kind of, sort of. And what I mean by that is that if you build a linear accelerator, the output energy is proportional to the length of the accelerator, and there's no real limit. You could just make the accelerator longer and longer. So you could imagine taking the largest linear accelerator in the world today, SLAC, which is 2 miles long and reaches an energy of about 40 GeV. And you could do a back-of-the-envelope calculation to ask yourself, how long would the accelerator have to be, if it's the same technology, to reach an energy of 10 to the 16th GeV? And you could all go home and check me, but when I did it, I figured that the length had to be 85 light years. Now, at the time, many of us were very disappointed that neither NASA nor the Department of Energy seemed to be interested in taking up this challenge. So what it meant is that if we wanted to see the most dramatic consequences of these grand unified theories, we were really forced to turn to the only laboratory to which we had any access to at all, which has ever reached those energies, and that is the universe itself in its very infancy. According to conventional cosmology, and inflation doesn't really change this, the universe would have had a temperature where the kT, the mean thermal energy, would have been 10 to the 16th GeV at a time of 10 to the minus 37 seconds after the instant of the Big Bang. So that drove us to be thinking about these unbelievably early times. And the results have been very interesting. It does seem to turn out that by combining ideas from particle physics with cosmology, new theories have been developed which seem to give a very good explanation for many of the properties that our universe has. And that's what I'll be talking about. Now, of course, the award is named for Isaac Newton, who's certainly, I think in the eyes of many, the greatest physicist who ever lived. Curiously, it comes at a time when my own wife, Susan, has made analogies between me and Isaac. I think the sign of my wife's comments were a little bit different from the IOP's. It came about when I was explaining to her about the multiverse and how I was working on this and talking about other universes and things. And she looked at me very quizzically, and then she sort of smiled and said, well, I guess it's OK. Newton worked on alchemy. So, to begin, I want to begin by talking about the standard Big Bang theory, the theory that existed basically before inflation was discussed. The theory is basically the theory that the universe as we know it began some 13 to 15 billion years ago. And now, in fact, we think we have a very precise estimate of that age, 13.7 plus or minus 0.2. I stuck in these words as we know it for good reason, because the 13.7 billion years comes from extrapolating backwards the universe that we see. And 13.7 billion years ago, it reaches some kind of incredibly hot, dense state, which naively looks like an actual singularity. But we don't really understand that singularity. The further back you extrapolate, the less reliable your extrapolation. So nobody claims to know for sure that the universe actually began 13.7 billion years ago. And in fact, I'll later be telling you in today's talk that inflationary models strongly suggest that the event that happened 13.7 billion years ago was not really the beginning of all of existence, but rather just our own local Big Bang in a much bigger multiverse which existed previously. In any case, though, 13.7 billion years ago, we are firmly convinced that the patch of matter that we now see was in the form of an extremely dense, uniform soup that filled space uniformly. This filled space uniformly part I'd like to emphasize. There's a common cartoon notion of the Big Bang as a tiny egg that was sitting in empty space and suddenly exploded. That is not, never was, the scientific description of the Big Bang. As far as I could tell, there's nothing illogical about the exploding egg theory compared to the normal Big Bang. It just doesn't agree with what we see. Because if you had an egg that exploded, unless we were right at the center, which seems highly implausible. If we were over here and the explosion was there, obviously when you look towards the explosion, you'd see an explosion. If you look the opposite direction, you'd see essentially nothing. And that does not resemble our view of the sky. When we look around in different directions, what we see is an essentially uniform distribution of matter. And we also look at the cosmic background radiation, which we view as the leftover heat of the Big Bang. And that's measured very precisely and is unbelievably uniform in its intensity in all directions. It's uniform to about 1 part in 100,000. The egg theory would predict that the sky should look very non-uniform, because when you look toward the egg, you'd see a hot spot. Opposite direction, you'd see a cold region. But that's not at all what we see. What we see is things look completely uniform. So in fact, the Big Bang theory posits that the initial space was uniformly filled with matter, no localized egg in an empty space. And this uniform distribution of matter was all expanding. All the bits of matter were moving away from the other bits of matter. And that's the scientific version of the Big Bang theory. And this is a very successful theory. It has very important abilities to explain features of our universe. In particular, it explains how the early universe expanded and cooled, and you could actually calculate how fast that expansion and cooling should take place in a very simple way. You can calculate how the light chemical elements formed, because this model started when the universe was so hot that even the nuclei of atoms would not have been stable. So the nuclei have to form later as the universe cools. This work was started by George Gamow and his collaborators back in the 1940s. And they, at that time, became very disappointed in the results and eventually gave up on it. And the reason was not that their calculations were wrong. Their calculations were approximately correct. But they were assuming that all the chemical elements had to be made in the Big Bang. And they showed that it was not possible, which was correct. Our current point of view is that most of the chemical elements around us were not formed in the Big Bang, but rather were formed much later in the history of the universe in the interior of stars. And then when stars explode, they spew these heavy elements out into space, ready to recollect into later generation stars like our sun. And only the latest chemical elements were produced primarily in the Big Bang. But that still gives about 5 different isotopes or so that one can measure and predict. And the predictions for the abundances agree very, very well with the measurements. Finally, the classic Big Bang theory allows us to describe how the matter in the universe congealed to form stars, galaxies, and clusters of galaxies. That's certainly still a work in progress. Nobody claims that we completely understand that, but it certainly seems to fit with the basic Big Bang picture. But what I want to talk about tonight is going beyond the conventional Big Bang theory. So let me move on to comment about a few of the things that the conventional Big Bang theory does not describe. In particular, in spite of the fact that the theory is called the Big Bang, which might make you think that it describes a Big Bang, the one thing that the theory literally says absolutely nothing about is the Big Bang. It says nothing about what banged, why it banged, or what happened before it banged. It says nothing about the bang. It is literally the theory of the aftermath of a bang. When the theory begins in its scientific description, it assumes that all of the matter already exists, all of the matter is already hot, all of the matter is already expanding outward. The explosion of the Big Bang had already happened before the theory begins. In a similar vein, the theory just says nothing about where the matter came from. It simply assumed that all the matter already existed, and existed in a particular state. In the conventional form of the Big Bang theory, for every particle that exists in the universe today, there was some precursor particle that existed right from the instant of when the theory begins to describe our universe. Now, you might be surprised that one can even talk about where the matter came from. But it turns out that in inflationary models, one can actually explain where essentially all of the matter in the universe came from, although not quite all. We'll be getting there soon. So let me move on now to describe how cosmic inflation changes our picture of the Big Bang. Inflation is a modification of the Big Bang theory. It does not throw away the Big Bang theory, because as I've told you, the Big Bang theory is, in fact, a very successful theory for describing many features of our universe. But inflation modifies the standard Big Bang theory. And the nature of the modification is, I think, well described by a word that I believe originated in Hollywood. It's the prequel. It's what came before the description of the Big Bang that was already part of the standard theory. And in particular, inflation can explain what I would refer to as the bang of the Big Bang. And by that I mean it explains the repulsive force that drove the universe into this period of gigantic expansion, which we call the Big Bang. And it does that in the form of what I consider to be kind of a miracle of physics. Now, of course, scientists have to be careful when they talk about miracles, because scientists, I think, aren't supposed to believe in miracles, or at least they're not supposed to admit that they do. But when I talk about a miracle here, I'm not talking about anything supernatural. But the way I look at it, there are certain properties of the laws of physics which are so surprising and so novel and so different from what most of us learned when we were in school that I think they just naturally seem to be something that you would want to refer to as a miracle. And inflation is really based on two of these miracles. And the first is the miracle of repulsive gravity. Gravity is not always attractive, but gravity can act repulsively. And this is known in the context of general relativity. Einstein himself made use of it in his earliest model of the universe, in which he introduced this cosmological constant to produce a repulsive gravitational force, which would prevent his universe from collapsing. Einstein believed that the universe was static, and he discovered that if you just had ordinary gravity, as described by general relativity, the entire universe would collapse. And not believing that that could happen, he introduced this repulsive gravitational force, all within the context of general relativity, to hold the universe up. And that repulsive force is something which can exist in many ways in general relativity. General relativity allows both kinds of forces to be produced as gravitational forces. In particular, according to general relativity, you can get a repulsive gravitational force if you have a material with a negative pressure, a material which actually has a pressure less than 0, which you can think of as a suction. And furthermore, particle theories tell us that you can create states of negative pressure, but in particular, states for which the energy is dominated by the potential energy of a scalar field are states that will have a negative pressure. And that's basically how inflation works. It's based on states which are dominated by the potential energies of scalar fields, producing negative pressures, which produce repulsive gravity, which cause the universe to rapidly begin to exponentially expand. So inflation proposes that at least a patch of this repulsive gravity material, this negative pressure material, existed in the early universe. It doesn't have to fill the early universe. It just has to have a patch of it. And we don't really know what energy scale inflation happened at. But a likely place at which it might have happened is at the scale of grand unified theories. And just to give you some sample numbers, I will use grand unified theories for my sample numbers. So if inflation happened at the scale of grand unified theories, this initial patch can be unbelievably small. It could be only about 10 to the minus 28 centimeters across. And that's enough to produce our universe from it. And it can be in the midst of a bigger space. It does not have to fill the space. Now, since any such patch is enlarged fantastically by the inflation, one doesn't really care about the initial density or probability of such patches, as long as one thinks that there's at least some possibility that at least one of them existed, and then our universe would come from that one patch. Once you assume that such a patch exists, the gravitational repulsion created by that patch becomes the driving force of the Big Bang. The patch starts to exponentially expand. The time constant of the exponential expansion would be only about 10 to the minus 37 seconds if we were talking about inflation at the grand unified theory scale. So every 10 to the minus 37 seconds, this region of space would double or multiply by e. To this accuracy, it doesn't matter which of those you say. And we'll keep doing that again and again. And to make it work, what you need is a total factor of about 10 to the 28, which only requires about 65 time constants. E to the 65 is about 10 to the 28. Now, you could have much more. You don't need to fine-tune the amount of inflation you have. It's perfectly OK if there's much more inflation than this minimal amount. But to make the theory solve the problems it's intended to solve, you need at least 65 time constants of this inflation. And that means that inflation needs to only last for about 10 to the minus 35 seconds, order 100 times the time constant, which was 10 to the minus 37 seconds. And at the end of that time, the region that will be destined to become our observed universe would still be small. It would be about the size of a marble, but vastly larger than the 10 to the minus 28 centimeters that it started. Now, inflation will end because this negative pressure repulsive gravity material is fundamentally unstable. So it decays, much like some radioactive substance decays. And when it does decay, it ends inflation. And furthermore, it releases energy when it decays. And that energy produces a hot soup of ordinary particles. And that hot, dense soup becomes the primordial soup of standard cosmology. So when the repulsive gravity material decays, it produces the initial conditions for the conventional Big Bang theory. The prequel ends, and the main movie begins. However, I should qualify this. There is a caveat. This decay that ends the inflation, and we'll be coming back to this point, happens in most places, but it does not happen everywhere. And the tiny regions which are left, which remain inflating, the rare regions that are left that remain inflating, turn out to be very important, and we'll come back to that. OK, now, a peculiar feature of this expansion driven by the repulsive gravity is that the energy density of this negative pressure repulsive gravity material is not lowered as it expands. If you had any ordinary gas expanding by this huge factor, it would thin out. It would dilute to zero energy density or incredibly small energy density. That does not happen during inflation. For the expansion driven by this repulsive gravity, the energy density actually remains constant as the expansion takes place. So even though more and more mass energy is appearing in this enlarged region of the repulsive gravity material, the claim is that total energy was still conserved, because total energy does have to be conserved. That principle is not going to be violated by anything that I'll talk about. And the way that works involves what I'm calling miracle number 2 of inflation. And miracle number 2 is the fact that although we are accustomed to the idea that any energy is a positive number, energies do not always have to be positive. Energies can be positive or negative. And in particular, the energy of a gravitational field is negative. And that's a statement that's true in Newtonian mechanics, and it's true in general relativity. Although in general relativity, there are some ambiguities about how you define it. But if you define it the way I'd like to define it, it's true in general relativity as well. In Newtonian physics, it's actually pretty easy for you to see it. Probably everybody knows how to derive the energy density of a Coulomb field. That's a standard calculation in freshman physics courses, and done in more sophisticated ways in graduate courses. And the energy density of an electric field is some positive number times the square of the electric field strength. And the value of that positive number depends on what units you use, of course. If you compare Newton's law of gravity with Coulomb's law, at first glance, they're sort of the same. They're both inverse square laws. But if you look a little more closely, you realize that they actually have opposite signs. Two positive charges repel each other. Two positive masses attract each other. And if you just do the same calculation that you would do for Coulomb's law for Newton's law of gravity, you can calculate the energy density of a Newtonian gravitational field. And the whole calculation is identical, but this minus sign carries through at each step. And you end up proving that the energy density of a gravitational field is actually negative. Intuitively, what that corresponds to is simply that if you were comparing this with electrostatics, to build a large electric field, you have to push charges together, and as you push them together, they repel each other, and you have to do a lot of work to push a lot of charges together. If you're trying to make a large gravitational field, you're pushing masses together, and you don't have to do any work to push masses together. They attract each other. You can actually extract energy as the masses pull towards each other. So you can create a strong gravitational field and take energy out at the same time, and that implies that the energy of the gravitational field must truly be negative. And that means that as the universe undergoes this huge expansion at a constant energy density, so more and more energy is appearing in the form of the matter that fills this region, it can be compensated by having more and more negative energy appear in the gravitational field, so that the total energy remains constant, incredibly small, and possibly exactly zero, which I think is the most likely energy given this picture. So the positive energy of the false vacuum was compensated by the negative energy of gravity, and the total energy of the universe may very well be zero. And false vacuum just means this repulsive gravity, negative pressure material that we've been talking about. OK, so that describes the mechanism of inflation. And I think I'm done describing everything I want to describe about the mechanism of inflation. But so far, I think all I've at best convinced you of is that inflation is a possible story about how the universe could have begun. But I want to do more than that. I want to try to convince you that there's a lot of evidence that our universe actually went through this history, that this really does describe the universe that we live in. And I want to, in particular, talk about three crucial pieces of evidence that our universe underwent this process of inflation. So the first is the large-scale uniformity of the universe. And in particular, the large-scale uniformity is indicated very strongly, observationally, from the cosmic background radiation, the radiation that we view as the afterglow of the heat of the Big Bang. That radiation, as I think I mentioned in my introduction, is known to be uniform in its temperature, as one looks across the sky, to the extraordinary accuracy of 1 part in 100,000. Now, I might mention, just to be complete here, that when you just look at the radiation, you actually see deviations of about 1 part in 1,000, not 100,000. But those deviations that you see at the level of 1 part in 1,000, we associate with the motion of the Earth through the cosmic background radiation. And that motion produces a particular pattern. We have no other way of measuring the velocity to this kind of accuracy. So one fits the motion of the Earth through the background radiation by looking at the pattern of radiation. It gives you a dipole. So one fits the best dipole, and that determines the velocity of the Earth through the radiation. You compensate for that. That's introducing 3 parameters, the 3 components of the velocity. And with those 3 parameters, you then ask, what are the residual fluctuations? The residual fluctuations you have to attribute to actual anisotropies of the radiation itself. And those residual fluctuations are what's at a level of 1 part in 100,000. So we believe the radiation itself really is uniform to this level, but we see a deviation in excess of that due to our motion through the radiation. Now, to understand what this means about the universe, I need to say a few words about what we think is the history of this radiation. And in particular, we believe the radiation was released at about 400,000 years into the history of the universe. And by released, what I mean is that prior to this time, the universe was so hot that it would have been a plasma. And plasmas are incredibly opaque to radiation. Roughly speaking, the photons constantly scatter off of the free electrons, which have a very high cross-section for scattering photons. So during the first 400,000 years of the history of the universe, the radiation was frozen with the matter. Even though each photon was moving at the speed of light at any given instant, each photon was constantly colliding with an electron and scattering and changing directions. And the net effect is that the photons really didn't go anywhere during the first 400,000 years of the history of the universe. But then at 400,000 years, the matter cools enough to become neutralized, and suddenly, or at least rather suddenly, the universe becomes transparent to these photons. And from then on, the photons just move on straight lines. And when photons move on straight lines, they form images, just like you see my face from the photons that travel along straight lines from my face to your eyes. Similarly, when we look at the cosmic background radiation, we're essentially seeing an image of what the universe looked like at 400,000 years after the Big Bang. So the conclusion then is that if the radiation looks unbelievably uniform, that means that the universe itself was unbelievably uniform by 400,000 years after the Big Bang. Now, what does that say about explanations of this uniformity? It says a lot, because when you do the calculations, and they're fairly simple calculations, what you find is that if within the context of this conventional Big Bang theory, you try to explain how the universe got to be so uniform, you'd have to explain how it got to be uniform by 400,000 years. And the point is that there's just not nearly enough time for information to travel from one piece of matter to another by 400,000 years to allow this uniformity to be established. So if you believe that the universe did not start out uniform, if you believe it started out uniform, I should specify that, then everything's OK. You could just put all of this into your assumptions about your initial conditions. But if you want to explain this uniformity, then you really cannot do it in the context of the conventional Big Bang theory. And the reason is simply that in the conventional Big Bang theory, the matter moves outward so quickly that there's not time, given the limitations of the speed of light, for the matter that goes this way to have communicated in any way with the matter that goes the opposite way. So there's no explanation for why they should be at the same temperature at the same time, which we know they were to this extraordinary accuracy of 1 part in 100,000. And to allow them to communicate would require the transmission of energy and information at about 100 times the speed of light. And nothing that we know of in physics allows that to happen. So within the conventional Big Bang theory, unless you start the universe out completely uniform, there's no way to explain the uniformity that we see. That's the problem. However, in inflationary models, that problem goes away completely in a very simple way. Inflation modifies this prehistory of the universe. And in particular, because inflation gives an acceleration to this expansion, it means that the universe can start out small and essentially hang out that way for a little while before inflation starts. And during that early period before inflation, there's plenty of time for the region that's going to become our observed universe to become uniform by the same kind of processes that a slice of pizza gets cool when you take it out of the oven. Things just come to the same temperature if they have enough time. And this region is small enough so there is enough time. Then inflation takes over and produces the accelerated expansion and magnifies this tiny speck to become large enough to include everything that we observe. So inflation provides a very simple and natural explanation for how the universe got to be so uniform. So that was item number one, the first piece of evidence that our universe actually underwent this process called inflation. The second issue I want to talk about, there are three I want to talk about. The second is what's usually called the flatness problem for reasons that you'll see shortly. It's basically the problem of explaining why the early universe was so flat. By flat, I of course do not mean two-dimensional, as sometimes audiences assume that I meant. By flat, I mean Euclidean, because according to general relativity, space-time is fundamentally non-Euclidean. But our universe is incredibly close to Euclidean, and why it's so close to Euclidean is basically what this flatness problem is all about. Now, according to general relativity, there are three possible geometries if you assume that the universe is homogeneous and isotropic, same in all places, same in all directions. And they are a closed geometry, which is like the surface of a sphere, an open geometry, or a flat geometry, where flat is the Euclidean case. And that's the case that we're very close to and what we're now trying to explain. According to general relativity, the flatness of the universe is related to its mass density. And cosmologists talk about a quantity called capital omega, which is the actual mass density, whatever it is, divided by what's called the critical mass density, where the critical mass density depends on the expansion rate. It's not a constant, but for a given expansion rate, there's a certain critical mass density. And the critical mass density is just defined as that density which makes the universe the flat case, which is the boundary of the two other cases. So if omega is equal to 1, it means the universe is flat. If omega is greater than 1, it's closed. If omega is less than 1, it's open. And the key point that makes this a problem is that omega being equal to 1 turns out, when you look at the equations of motion, is an unstable equilibrium point of the evolution of conventional cosmology. And that means it's like a pencil balancing on its tip. If it stays exactly straight up, that's a solution to the equations of motion. It can, in principle, stay exactly straight up forever, talking about a classical pencil. But if the pencil is leaning just a little bit in any direction, it will rapidly start to fall in that direction. And that's the same way that omega behaves with respect to omega equals 1. That is, if omega is exactly equal to 1, it will stay exactly equal to 1 forever. But if omega in the early universe were slightly below 1, it would rapidly fall towards 0. And no galaxies, for example, would form. Lots of other things would be different, too. The universe would just dilute to 0 density very quickly. On the other hand, if omega in the early universe were just slightly greater than 1, omega would rapidly rise towards infinity, which would mean the universe would reach a maximum size, turn around, and collapse. And all of that would happen rather quickly if omega were greater than 1 in the early universe. To be as close to the critical density as we measure today, if we go back to, say, 1 second after the Big Bang, omega must have been equal to 1 at 1 second after the Big Bang to an accuracy of 15 decimal places. And that is the heart of this flatness problem. Conventional cosmology can only work if the initial value of omega was equal to 1, initial meaning at time 1 second. Can only work if omega at time 1 second was equal to 1 to 15 decimal places. But there's nothing in the theory that causes omega to have that value. You just need to put that value in by hand if you want the theory to, in the end, describe our universe. So if you're going to just assume it started that way, there's no problem. If you're going to just make up initial conditions in a fine-tuned way, you can make this work. But if you want to have any explanation for why the universe looks the way it looks, this conventional Big Bang theory doesn't work. It just tells you that you need omega to have started out extraordinarily close to 1, but it doesn't give you any reason why it should have started out incredibly close to 1. The inflationary model solves that because during inflation, gravity behaves very differently. It behaves repulsively, and that turns all kinds of things around. And in particular, it turns around the behavior of omega. So instead of omega being driven away from 1, during inflation, omega is driven towards 1. And it's driven towards 1 with incredible rapidity. So a very short period of inflation, like the one that we talked about, 65 e-folds, is all that you need to arrange for omega to be as close to 1 as it needs to be, even if it started out rather far from 1. So omega could start out being 2 or 10 or 1/10 or 10 to the 5 or 10 to the minus 5. The further you start from 1, you need a little bit of extra inflation to drive you to 1 sufficiently. But because the effect is exponential, you don't need a lot of extra inflation to drive omega to 1. Now, this turns out to actually give a prediction. You could avoid this prediction if you arranged for inflation to end at just the right time. But because omega is driving, because inflation is driving omega to 1 so quickly, unless it ends just at the right moment, it will drive omega very, very close to 1, much closer than it needs to be to just explain current observations. So the prediction is that omega today should be 1, that even today we should have a critical density, that the mechanism which drives omega to 1 overshoots and produces not something that just approximately 1, but should really be almost exactly 1 even today. Now, for much of the history of inflation, that was a problem because some years ago, the astronomers thought that the value of omega was 0.2, 0.2 or 0.3, and that made it very difficult. For example, when I had dinner with astronomers, they would say things like, well, you know, inflation is a pretty theory, but it just doesn't fit the data because it predicts omega is 1, and we know omega is not 1. It's only 0.2 or 0.3. Fortunately, all that changed about 10 years ago. And the latest number, which comes from data from the WMAP satellite combined with the 2-degree field survey and the Sloan Digital Sky survey and the supernova data to put all this together to get the most precise estimate of omega that people know how to make. And that's it. And this is an experimental number, not a theoretical number. And now omega is 1, just like inflation predicts. So it's a big success. Now, it wasn't so much that the astronomers were completely wrong. What happened is that a new ingredient got added about 10 years ago. And the new ingredient is what's called dark energy. And it comes from the fact that in 1998, astronomers discovered that the expansion of the universe is not slowing down under the influence of gravity, as everyone had expected, or almost everyone had expected up until that point. But in fact, the universe today is actually accelerating. And in fact, it's been accelerating for about the last 5 billion years or so. And that, in fact, means that there's a kind of repulsive gravity going on in the universe today. We don't know of any other explanation for this other than some form of repulsive gravity. And the stuff, which again has to have a negative pressure, that drives this repulsive gravity, we don't know exactly what it is, so we call it dark energy. So dark energy is the energy that, by definition, the energy that's causing this expansion. And even though we don't really know what the dark energy is, we can, in fact, figure out how much of it there has to be to produce the right acceleration. And it's by adding in that extra energy from the dark energy that brings omega up to 1 from the previous value of 0.2 and 0.3. So the astronomers were, in fact, right about the contributions to omega from the things they were looking at. But it turned out that there's, in fact, the larger contribution to the total energy of the universe in the form of this dark energy, which was not discovered until 10 years ago. Finally, and perhaps most impressively, inflation makes a prediction for the small-scale non-uniformity of the universe. Remember, point 1 was the large-scale uniformity. On the larger scales, the universe looks unbelievably uniform. But of course, on smaller scales, like this room, there are lots of non-uniformities, also on the scales of galaxies and things like that. The cleanest way to measure these non-uniformities is in the cosmic background radiation, because it's essentially unprocessed in the cosmic background radiation. It hasn't had time to undergo nonlinear and complicated evolution. And even though I told you that the intensity of the cosmic background radiation is unbelievably uniform to 1 part in 100,000, that's not a bound. The astronomers actually see non-uniformities at the level of 1 part in 100,000. And now they can even measure those non-uniformities with rather fantastic precision. And one naturally wants to ask, where did these non-uniformities come from? Now, in conventional cosmology, that is without inflation, there was really nothing that could be said about it. Without inflation, the initial conditions were really whatever you made them up to be. So there were initial ripples if you put in initial ripples. If you didn't put in initial ripples, there were no initial ripples. There was no theory that controlled how those initial ripples might be created. In inflationary cosmology, there's a different answer. Inflation can actually attribute these ripples to quantum fluctuations. At the classical level, inflation simply smooths the universe out by this enormous expansion. The effect of an enormous expansion is to smooth everything out. But the world is not classical. The world is quantum mechanical. And when one puts in the quantum fluctuations to describe inflation, then you would expect that the mass density would, on average, be uniform. But because of quantum fluctuations at any given place, it could be a little bit above the norm or a little bit below the norm. And you can actually calculate the properties of these density fluctuations and compare with observations. So inflation allows us to understand these ripples in terms of quantum fluctuations. Now, I should add that usually we think of quantum fluctuations as being important only at incredibly small distances. We're not used to quantum fluctuations being relevant in the room or the things that we see classically. What makes it different for inflation basically is the exponential expansion again. This exponential expansion is constantly stretching quantum fluctuations at very, very small microscopic wavelengths upwards to get bigger and bigger into macroscopic and astronomical dimensions. And if this is right, it would mean that our whole galaxy is just a quantum fluctuation, which is a bizarre concept, but it seems to work. And I'll show you how well it works. Our best data comes from the WMAP satellite so far. The Planck satellite is now in the air and collecting data, but we don't have that data yet. here's a picture of an artist's conception of the WMAP satellite. That's David Wilkinson, for whom the satellite has been named. Here's the data. It's my favorite graph in the whole world. This is a graph of the temperature fluctuations as a function of the multipole. That is, they expand the temperature pattern that they see in the sky in spherical harmonics, and you talk about the intensity for each value of L that corresponds to those spherical harmonics. You could think of it as an angular wavelength, and I've tabulated on the top as in angular wavelength units, where these are degrees. That's 0.2 degrees corresponding to a very high L. Low L corresponds to a large angular wavelength. So 180 degrees is way down here, corresponding to L equals 2. And the black lines and black dots represent the data, mostly from WMAP, but on the right-hand side at shorter wavelengths, other experiments do better. So this includes the CBI, Akbar, and Boomerang experiments. The most impressive part is on this first peak, where those little dots with their sizes, their error bars, and there's just an absolutely gorgeous fit between the experimental data and the red curve, which is what you predict based on inflation, including lambda means including dark energy, excuse me. Lambda is a stand-in for dark energy. So this is a fantastic graph. Now, to make it a little easier to tell how impressive this graph really should be, we've also added to the graph curves representing other theories, just to make clear that it doesn't come out automatically that you get these things right. So if we had an open universe with omega being 0.3, like the astronomers thought 10 years ago, then you get this yellow line, which, as you see, doesn't fit the data at all. Another competing theory that for maybe a decade or so was viewed as a competing theory for inflation for the generation of these density fluctuations involves the creation of cosmic strings in the early universe, which would form at a phase transition, and the randomness of that phase transition would produce density fluctuations. That produces this purple curve, which again looks absolutely nothing like the data. And finally, we put in, for one more comparison, what inflation itself would give if instead of having dark energy, you let omega equal 1 by putting in more dark matter. And that gives this light green curve, which again bears no resemblance to the data. So the bottom line is that inflation fits the data absolutely gorgeously, and none of these other options do. For the sake of truth in advertising, I should mention that there is one theory that is actually a lot like inflation, but is sometimes viewed as an alternative to inflation, namely something called the ekpyrotic cyclic model, which, at least according to some calculations, they're actually contradicting calculations, but according to some calculations, gives exactly the same answer as inflation for this problem. So inflation might not be the unique theory that does this. OK, this is a more recent set of data from WMAP, just to show you that it continues to be a good fit. And this is the curve which shows the same WMAP data, but with different high-frequency data from other experiments, again showing a gorgeous fit. OK, now I want to change gears. I've now tried to explain what inflation is, tried to explain why we think our universe, why at least some of us think, including me, that our universe began with a period of inflation. Now I want to talk about dark energy and the role that plays in motivating this idea of a multiverse, which I'll also be talking about. So dark energy, I mentioned before, it was discovered in 1998 by two large groups of astronomers that the universe has been accelerating for about the last 5 billion years out of the 13.7 billion years of its history. And an implication is that inflation of a sort is really happening today. That is, we have accelerated expansion, presumably driven by some material with a negative pressure. However, it's not the same as the inflation in the early universe. It's much, much slower. The energy density of this negative pressure material is clearly much less than the energy density of the stuff that drove inflation. Now, this stuff that is driving the expansion today is called dark energy. And you might ask, what is the dark energy? There is a very succinct answer to that. Who knows? We don't know what it is, which is why we call it dark energy. But there is a simplest candidate, and other options are really very similar. So we do know a lot about this dark energy, even though we don't know what it is. The simplest option, which is the one I'll discuss, is the option that is just plain vacuum energy, which is synonymous with a cosmological constant. Einstein introduced this cosmological constant as an extra term in his field equations, and he introduced it precisely for the purpose of describing a repulsive gravitational force. To Einstein, the vacuum was empty. He was not really a quantum physicist. He was really a classical physicist. So to Einstein, it was not really conceivable that empty space should have weight, should have mass. So when he added this term, he just viewed it as an extra term in the equations that described how gravitational fields are produced. However, in the modern context, we look at it differently. Looking at exactly the term that Einstein put in those equations, you could interpret it as an extra contribution of matter. And if you do, it's just energy density of empty space. And it leads to exactly the same equations. And that's the modern interpretation, that the cosmological constant is synonymous with vacuum energy. From the modern point of view, the vacuum is not empty. It's a quantum vacuum with quantum fluctuations going on all the time, particles appearing and disappearing. You have fields in the vacuum, Higgs fields with non-zero values. The modern vacuum, the vacuum known to modern particle physics, is an extremely complicated state. And there's no reason why it should have zero energy density. So we're perfectly happy to attribute a non-zero energy density to it. So the cosmological constant becomes that. Nonetheless, even though we can glibly say that this is vacuum energy and feel that that's a plausible statement, it really is a nightmare when we try to understand it in detail. What's a nightmare is to try to understand the magnitude of this horrible dark energy. And here's the problem. The quantum vacuum, as I said, is far from empty. So the mere fact that we're assigning a non-zero energy density to the vacuum is no problem. That seems completely plausible. But we can ask what happens if we try to calculate what that vacuum energy density should be using our quantum picture of the vacuum. So in a quantum field theory, one can calculate the energy of quantum fluctuations. The problem is it diverges. The divergence comes from very short wavelength fluctuations. If you imagine talking about the quantum fields in some box, where one makes up a box just to make the problem finite, inside that box one can describe the electromagnetic field in terms of normal modes. Each normal mode contributes in energy 1/2 h bar omega. It acts like a harmonic oscillator to the vacuum energy. And the problem is just that there's no shortest wavelength. There are always shorter and shorter wavelengths, higher and higher omegas, making the sum just grow and grow and grow in the context of a quantum field theory, growing without bound. So in a quantum field theory, the vacuum energy just diverges. But one could say that that just means that the quantum field theory should not be trusted down to very, very short wavelengths. After all, we developed this quantum field theory by doing experiments and so on, and those experiments had some finite size. We don't know the physics down to arbitrary short size scales, so it's very natural to cut off that infinite sum at some short wavelength using the excuse that you don't believe that you have any right to extrapolate the physics beyond that short wavelength. So you get to choose what the wavelength is. A common number that people use, because it seems to make some sense, is to say that we believe physics, we believe that quantum field theories work, except for quantum gravity effects. We're pretty well aware that we don't really understand how to put quantum gravity into these theories. And one could say that that's the place of ignorance where we should cut off our sum. So let me just pursue that. If you do that, it means cutting off at the Planck energy, 10 to the 19th GeV, which is the scale of quantum gravity. And if you use that cutoff, you can then get a finite number for the vacuum energy density. But the problem is that the number you get is too large, and it's not just a little bit too large, it's too large by about 120 orders of magnitude. And that is an embarrassment, even for cosmologists. And this is the nightmare of dark energy. We have no way of understanding at the present time why the actual energy that we observe is so incredibly small compared to the estimate that we make naively of how much energy we might expect the vacuum to have. Now, even if you don't use the Planck scale, if you cut off even at the electroweak scale or any scale associated with particle physics, you get a number that's vastly too large. Not necessarily 120 orders of magnitude, but nonetheless still vastly too large. The problem is there's just a big mismatch between the energy scales of particle physics and energy scales of cosmology. This cosmological constant is very significant on the energy scales of cosmology, but that's still very, very low energy compared to any energy scale that's relevant to particle physics. Let me leave that for now as a mystery, and let me come back and talk about inflation, because there's a feature of inflation that I have not yet talked about here that turns out to be relevant to this issue, at least from the point of view of many people. And that leads us into this multiverse picture. I told you that this repulsive gravity material is unstable so that it decays. And it is indeed true that if you sit in any one location inside this repulsive gravity material and watch what happens, with probability 1, sooner or later, usually in a fairly short time, you will see it decay, because the probability of it not decaying falls off exponentially with some time constant. And if you wait some numbers of those time constants, the probability that has not decayed just gets unbelievably small. So in any one place, you expect inflation to end if you just sit in one place and wait. However, the catch is that while this repulsive gravity material is decaying, it's continuing to exponentially expand. And the exponential expansion is, in fact, vastly faster than the decay. If that were not the case, you would not have a successful inflationary model in the first place. So if you wait, for example, for one half-life of the decay, half of it will have decayed, but the half that remains will be vastly larger than what you started with. So you're not making any progress towards ending inflation permanently. Rather, the inflating region just gets larger and larger and larger with time, even though it's decaying. So it's a very peculiar picture, but this is the picture of eternal inflation. Once inflation starts, it just never stops. The volume that is inflating increases with time, even though the inflating material is decaying, because it's exponentially growing faster than it's exponentially decaying. So the inflation becomes eternal. Once it starts, it never stops. The inflating region never disappears, but instead pieces of it undergo decay. And when each piece decays, it produces a local universe, a local Big Bang. And each such local universe is called a pocket universe. And we would be living in one of these pocket universes. These pocket universes are not small, but there are many of them. In fact, in this model, there'd be an infinite number of them. So instead of just getting one universe, inflation actually produces an infinite number of universes for the same price. So it's a real bargain. And that is the multiverse. And almost all models of inflation have this property, that once they start, inflation never stops. And instead of producing just one universe, you produce a multiverse. Now that plays into another idea coming from another area. Michael promised in his introduction that I was going to talk a little bit about string theory, and he's right. So here's the string theory part. Now, I don't know much string theory, I should add, so all of this is really just hearsay that I learned from my colleagues. But nonetheless, my colleagues seem to agree pretty much on what the story is. Since the inception of string theory, theorists have sought the vacuum of string theory, but they were never able to find such an animal. And within the past 10 years or so, almost all string theorists have come to the belief that the reason they've been unsuccessful in finding the vacuum of string theory is that there is no such thing as the vacuum of string theory. Instead, string theory is believed to have a huge number, and 10 to the 500 is the number that gets bandied about. I don't think you should take that number too seriously, but some huge number of long-lived metastable states, any one of which could serve as the substrate for a pocket universe. And this huge set of metastable states is what's called the landscape of string theory. Now, if you have eternal inflation like we just described, eternal inflation can presumably produce an infinite number of pocket universes involving every one of these 10 to the 500 different kinds of vacua. So inflation populates the landscape, produces pocket universes connected with each type of vacuum. Now this leads to very peculiar consequences, because even though we're assuming here that the laws of physics ultimately are the same everywhere, governed by this fundamental string theory, because each pocket universe is built around a different vacuum, the low energy physics of each pocket universe, the physics that is like the physics that we measure, would be completely different from pocket to pocket. Because the physics that we see is really just the physics of small perturbations about our vacuum. So things like the value of the Higgs field in our vacuum determine completely properties of particles that we measure. And all of the properties of the vacuum would play the same role as the Higgs fields do. So the low energy laws of physics could be completely different from one pocket to another. And in particular, the vacuum energy can be different from one pocket to another, because vacuum energy is one of the consequences of the interactions of the particles, which would vary from pocket to pocket. So that allows a new view of this cosmological constant problem, the problem of trying to understand why the vacuum energy that we measure is so vastly smaller than what we would expect it to be. It involves the idea of what's sometimes called the anthropic principle. People who like it and try to defend it sometimes call it environmental selection instead. That has a healthier sound to it than the anthropic principle, which has been mired in mud for many years. But here's the idea, and I'm going to advocate this as something that you should consider, something which could be the right answer. I'm not going to try to persuade you that it is the right answer, but I will try to persuade you it's a possible answer. I really think that there's nothing wrong with it. It could be the right answer. And I want to begin by talking about an alternative situation where I think we really would believe that the anthropic principle is the right answer. So let me, instead of talking about the cosmological constant, talk about the local value of the mass density. And by local, I mean, take a sphere around yourself of 10 kilometers and call that local and ask what's the average mass density in that sphere that's 10 kilometers about you. The answer is certainly on the order of 1 gram per centimeter cubed. That's sort of the density of matter around the Earth. If you compare that with the average density of matter in the universe, it turns out that that's actually about 10 to the 30 times larger than the average density of the universe. So it's fair to ask yourself, when I measure the mass density, why don't I get a typical value for the universe? Why do I instead get a value that's 10 to the 30 times larger than what I know is typical for my universe? Well, why is that so? Is it chance? Is it luck? Is it divine providence? Well, I think the answer here, as I hinted before, is the anthropic answer. I think most of us would presumably accept this as a selection effect. That is, we would assume that life can only evolve, or at least strongly preferentially evolves, in those rare regions of the universe where the density of matter is unusually high. So we don't worry about the fact that the mass density we see around us is 10 to the 30 larger than the average mass density. We just say that that's a natural consequence of the fact that life forms in those regions. And if you accept that, you've accepted the anthropic principle, whether you like it or not. So how does that play out for the cosmological constant or the vacuum energy density? Well, the history goes back to 1987, when it was actually Steve Weinberg who pointed out that perhaps the cosmological constant could be explained this way. The idea is that the cosmological constant, otherwise known as the vacuum energy density, maybe it is huge in most pocket universes. However, we should remember that this vacuum energy density really does affect the evolution of these universes. A very large positive cosmological constant causes the universe to fly apart. It produces a strong repulsive force. A very large negative cosmological constant, it could have either sign, would cause the universe to rapidly implode and collapse. So if, for example, we insist that our universe be capable of producing galaxies like the galaxies in our universe, then there's only a very, very narrow range of vacuum energies that allow that to happen. And that's basically what Weinberg was talking about. He was using galaxies as a criterion for the formation of life. If there's no galaxies, there's no life, he assumed. And if you grant yourself that assumption, then you're forced to conclude that life would form only in an incredibly small fraction of these universes, only in those very rare universes, those very rare pocket universes, in which the vacuum energy density was incredibly small compared to the average. In 1998, Steve teamed with Martel and Shapiro to do a more serious calculation of galaxy formation in universes with different values of the vacuum energy. And they concluded that within a factor of maybe 5 or so, they could explain why the cosmological constant is as small as what we measure. So this is the anthropic explanation of the cosmological constant, or the dark energy. Now, I won't say that this is without controversy. There's a lot of controversy about this. Many physicists regard this anthropic argument as totally ridiculous, having nothing to do with science, they think. I disagree. However, I would recommend that this anthropic explanation should be considered the explanation of last resort. It's certainly not something you really want to jump onto until we really understand the landscape of string theory, which we don't, and until we really understand how to know where life will form and where it won't, which we certainly do not understand now. The best we can do is to give plausibility arguments for these anthropic explanations. And therefore, I would say that an anthropic argument becomes attractive only when the search for a more deterministic explanation has failed, as has so far been the case for the cosmological constant. I might mention that anthropic arguments are also discussed for other quantities in physics besides the cosmological constant. For example, the Higgs mass, the top quark mass, and the magnitude of the density perturbations in the early universe. So this idea has gotten bigger than just an explanation for the cosmological constant. So is it time to accept this, what I'm referring to as an explanation of last resort? Well, I would just like to say that your guess is as good as mine. I'm not going to try to tell you what you should believe. But for the cosmological constant, I would argue that it's certainly time to take this idea seriously, I think, just because we have had so much trouble finding any other explanation. So I would say it's hard to deny that as of now, the selection effect explanation is by far the most plausible explanation that is known for the very small vacuum energy that we have been observing. Now this, to me at least, is very disappointing because I had always hoped that pure thought and theoretical physics would be able to ultimately predict what our universe should look like. And there was a strong hope for that in the early days of string theory, where people hoped that string theory would allow us to ultimately calculate all of the parameters of the standard model of particle physics. That would be great if it happened. But if this landscape picture is correct, it could really mean that all of the parameters of the standard model have the values that they have just out of historical accidents. It's the vacuum that we happen to fall into, and in different vacua they would have different values, and there would be no way to predict what the value would be, and that would be disappointing. It has been pointed out by enthusiasts of the anthropic principle that this would not be the first time such a thing has happened in physics. An analogy that's often used is to go back to Kepler. Kepler thought that the radii of the orbits of planets was a fundamental quantity that should be calculable. And he thought about models of regular solids embedded in regular solids. And that made sense from his point of view, because from his point of view, the solar system was the ultimate universe. It was the work of some god, and it should obey mathematical rules. So it should be possible to calculate the radii of the planets. But now we regard all of that as total nonsense. We do regard the radii of planets as just being historical accidents. And we've gotten over that. We don't fret anymore about the fact that we can't predict the radius of the orbit of Pluto. We just take the measured value from our tables and accept that and go on and do different problems in physics. So it's possible that the mass of an electron is the same way, that eventually we'll get used to the idea that the mass of an electron is not something fundamental that we should try to predict, but rather just some historical accident like the radius of the orbit of Pluto that we just have to measure and accept. So that's really all I want to say, but now I'll summarize just to make it clear what it is that at least I think that I've said. So what I think I've said is, first of all, that the inflationary paradigm is in great shape. Inflation can explain why the universe is so smooth and homogeneous when averaged over large regions. It can explain why the mass density of the universe is so close to the critical value. And it can also explain the ripples that we see in the cosmic background radiation. So it explains the large-scale uniformity. It explains why the mass density ratio omega was equal to 1 to 15 decimal places at 1 second after the Big Bang. And it predicts correctly that omega is equal to 1 today, where we know, in fact, that that is true to within an accuracy of about 1%. And finally, it explains very accurately the ripples that we see in the cosmic background radiation, explaining those ripples as quantum fluctuations that took place during inflation. Then we come to this idea of the multiverse. And if you've counted while I was talking, basically I would summarize what I was saying by saying that there are 3 winds that are blowing us towards believing in the multiverse. None of these prove that there's a multiverse. I'm not claiming that we can prove that there's a multiverse. But there are really 3 different arguments, all of which seem to be leading in the same direction. First, from inflation itself, almost all inflationary models are eternal into the future. That is, once inflation starts, it never stops, but instead goes on forever, producing pocket universe after pocket universe. On a completely separate thread, starting from string theory, string theorists almost all agree that string theory has no unique vacuum, but instead a landscape of perhaps 10 to the 500 long-lived metastable states, any one of which could be our vacuum. And finally, the thing that I think really drove large fractions of the physics community to think seriously about these anthropic arguments is number 3, the discovery by astronomers that the universe today is accelerating, which forces us to deal with this issue of a vacuum energy, and a vacuum energy which is non-zero but unbelievably small compared to anything that we understand. So one convenient explanation is this anthropic argument, which says that perhaps we see a small vacuum energy density simply because conscious beings only form in those parts of the multiverse where the vacuum energy density is incredibly small. And therefore, it's not surprising that we, as conscious beings, observe a very small vacuum energy density. The ultimate bottom line of this, though, is I think we don't really understand all of this. This could be the right answer, might not. But we've never had a model of the universe that works so well and that we could explain so many features of the universe, but at the same time is so mysterious because we really can't make sense out of this dark energy. Thank you.